Hi all, this is Lakshmi, working as Assistant Professor in the Department of ECE at SNSCT. So today I'm here to discuss about the lecture series on BJT biasing techniques. In the previous session, we have discussed about the fixed bias technique and the collector to base bias technique. And here, let us discuss in detail about voltage divider bias. So, from the name itself, it is clearly understood that the voltage is getting divided here. So, you can see that. So, this is the circuit of voltage divider bias. So, VI is the input voltage. So, we have the input capacitance. We could see that the input voltage here is getting divided between two series resistance R1 and R2. And so due to this, instead of giving negative supply to the emitter resistance, so this voltage division would provide a emitter resistance a ground such that it can increase the base voltage. So due to which any increase in the collector current would be compensated. And this type of biasing is the best thing because the stability is high in this type of biasing compared to the other type of biasing methods. So what happens here is the voltage which is getting divided between two series resistance R1 and R2. So instead of using the negative supply to the emitter, this voltage division would make it ground such that the base voltage increase so that any further increase in the collector current would be compensated. And the current and the voltage here are nearly independent of any variations in beta. So this is about voltage divider biasing. So now let us do the analysis here. So here there is an voltage source and there are two series resistance where the voltage is getting divided. So we can convert this into the Thevenin's equivalent circuit. So we have the supply here VCC and the two resistance, and we have the emitter resistance which we have converted here with Thevenin's equivalent circuit. So with the help of this Thevenin's equivalent circuit, we can do the approximation and analysis. So we know that the Thevenin's resistance, that is RTH, is here. We are replacing it with the parallel combination of R1 and R2. That is called as Thevenin's resistance. And ETH is given as the voltage across this resistance R2. So according to voltage division rule, we can calculate this voltage across R2 as the corresponding resistance multiplied by the opposite voltage, that is R2 VCC, divided by the sum of resistances, total resistances. So this is called voltage division rule. So we obtain VR2 as R2 VCC by R1 plus R2. And now coming to Kirchhoff's voltage law. So which is indicating that the algebraic sum of voltages around the closed loop is equal to 0. So according to Kirchhoff's voltage law, we could see that ETH minus IB RTH, so that is our Thevenin's resistance, minus VBE minus IE RE is equal to 0. So from this equation, solving for IB, we would obtain this equation, and we can solve for VCE by applying Kirchhoff's voltage law at the output loop. And the approximation of all these parameters could be obtained with the help of this approximated Thevenin's circuit. So when I consider my base current to be less than I1, this one, across R1, and when I1 is approximately equal to R2, we could write our VB, that is the base potential, as the opposite resistance into opposite voltage divided by the sum of the resistance. And when beta Re is greater than 10 times of R2, we would obtain these variations, that is IE is equal to VE by Re and VE is equal to VB minus VBE. And again from Kirchhoff's voltage law, the VCE at the output side, we can obtain VCE value as VCC minus IC into RC plus RE. So this is the approximated analysis. So today's assessment is draw the circuit of voltage divider bias. So for biasing of BJT, first we draw the BJT, then we are giving the input signal for amplification. So we have to do voltage division here. So two series resistance are connected where the supply is given here. We have the collector resistance and emitter resistance for stability. So this is the circuit of voltage divider bias. Thank you.